elongated structures within the image. Then we will threshold these images, meaning that we go to a binary representation. So we have a black and white image, where white represents this elongated structure we detected, and black is nothing more than the background. And each of these binary images is then combined into our final result. So here you can see that we nicely detected the cracks from this image. A second method is based on what we call the morphological black top hat transform, and it's a method that is being used a lot in the context of crack detection. And it works as follows. First, we have a grayscale representation of our colored patch. Then we apply what is called closing, and this is basically an operation that removes details of a certain size out of our original image. So you can see that this is a very blurred version of our original grayscale. So we take the difference of those two, and then we see that we nicely emphasized all the details, in this case the cracks out of the image. If we threshold that, this is what we get. So this works very well in case of very simple examples where there are no other objects than cracks within the image. But for example, here this is a part of the Ghent altarpiece. It's a detail of a book within the Ghent altarpiece, and you can see that we have a lot of other objects present in that image, and just applying morphological component black top hat transform, does not work. So we do apply black top hat transform, but multiple times, and we detect objects of increasing size. So here we detect small objects, and here we detect larger objects. We clean up those binary images by removing isolated pixels. We connect components that are supposed to be connected to each other, which gives us these cleaned versions of these binary images. With the objects of the small scales, we create what is called a base map. And we construct our final crack map by connecting the components of the coarser scales that we connect them to those of the base map. So this has the following advantage. So you can see here a detail where one of these letters within that book could be seen as a crack, for example. You see that here it is detected at a large scale, but it is not present in this base map. So when constructing our final binary image, you can see that we do not take this annoying detection false positive in our final result, which is exactly what we wanted to do in the first place. For the third crack detection method, we asked ourselves the question, does there exist a crack dictionary, an optimal crack dictionary? As far as we know, no. But we do know that there are dictionary learning methods where we can learn the atoms that are used to optimally represent those crack images. So for example, here we identified the atoms that are used the most to reconstruct this training image. And then we apply this, we reconstruct, for example, this image using that dictionary, and this is what we get. When we threshold that image, you get something like this. And this is a superposition on the original. So you see that we nicely detected the cracks within our painting. The problem with the three techniques I just mentioned is that they have a tendency to also detect other elongated objects within the images. So for example, here you have eyelashes, eyebrows, a mustache. So here we detect these as well. We mark them as cracks, which is obviously not something we want. So we need a post-processing step that is able to remove these cracks. So here you see that we more or less did a good job, except for here, where we still see as part of the mustache as being a crack. And then finally, we combine those three binary images with a merging algorithm, which gives us our final result, our final crack detection result. Let's move on to the multiple modality case, and this is again that part of the book, but now under acquired with different technologies. So we have the visual macrophotography, the infrared macrophotography, and an X-ray taken of the same part of that painting. Now, before we can use all this data together, we can do crack detection on them. We need to what we call register them, which means that we have to spatially align all those images. Every pixel that corresponds to each other should nicely overlap. So, and this is called registration. And the problem in this case is that our images look so different that we cannot directly apply a registration transform to them. But we did notice that a component that is more or less consistent in all these images are the cracks themselves. So we add an intermediate step, where we detect the cracks in each of these images, and instead of applying the registration algorithm on our original data, we apply it on those crack maps. And this gives us the transform coefficients that are necessary to apply our transformation and to nicely register all our data. So the workflow for the crack detection in the multiple modality case works as follows. Again, some pre-processing and the registration step I just mentioned. Then for each pixel in each of these modalities, we will extract a number of properties, features, which can range from pixel intensity values, color values, various responses to filters, again the black top hat transform I talked about, and many others. Then there is a training phase where we will try to model the conditional probability for each of these pixels, given their features that we extracted in the previous step, for them of being a crack or not. And once we train that model, we can feed our pixels, every pixels of the image to it, and the result is what we call a probability map. So now each pixel has a probability for it being a crack or not. So if we want a binary representation of that, like we had before, we just decide to threshold that image, which gives us this nice crack map. This is one of our results. So in this case, we fed the features we extracted to a random forest classifier, which is considered to be one of the state-of-the-art classifiers in the literature. And this is the result. This is when we apply it to our technique, and you can see that they're very, very similar. But our method has a tendency to produce finer cracks, and has a significant advantage that once that this model is trained, it's considerably faster. So this is another example where here you can see the crack detection based on random forest classifier, and here is our method where we slightly detected more cracks in the area of the eye of this portrait. And this image is meant to show you that even in very busy images that contain a lot of objects, we're still able to detect most of the cracks. So what are the applications now for these crack maps, for these binary images? Well, we have two cases. On the one hand, we can use them as the input to a digital restoration algorithm, which is done by means of in-painting. The in-painting algorithm was developed at the Ghent University by Tijana Ruzic, who is here somewhere today. But in this, so this is a part of the old data set, and there we had an additional problem. So detecting the cracks was not enough. We also had these bright borders on the side of the cracks, and if we do not detect them, if we do not include them in our in-painting, this gives us very bad in-painting results. So we needed to find a way to detect those as well. And here you can see a result where the yellow marked areas are the bright borders we detected within that image. So, and this is the results of in-painting. So here you see the original, and here you see the in-painted results without using the information from these, without including these bright borders. And this is a result when we include the bright borders. So you can see that there is a significant difference. And here the idea, the rest of the in-painting was done with the idea to improve the legibility of the book to aid paleographers in their studies. We did the same thing on the newly acquired images of the altarpiece. And for example, this is the original. Here you can see the in-painted version. And here is a detail where you see that we nicely filled in all of the cracks. Another possible application for crack detection is using them as a support tool during restoration of the altarpiece. So for example, here you see the crack map of that detail I showed before. We can do various processing on that. And here is an example where we calculated the densities of these crack patterns within the image. So the red areas correspond to high density zones, zones with high crack density. And the blue areas are zones that have low crack densities. So we can nicely mark those zones. For example, these are the zones of highest crack density in that part of the painting. And here are the areas of low crack density zones. And these corresponds to, so you cannot see them on the painting themselves, and this corresponds to over-painted damage in the Ghent altarpiece. So we plan to use them during the restoration of the altarpiece. Then let's move on to the last topic of my talk, which is on art forensics. And there the first topic I want to talk about is the classification of canvas. Traditionally, canvas paintings can be studied for authenticity and also for dating of these paintings. Traditionally, the X-rays of these paintings are studied, where an art specialist will count very tediously with a magnifying glass. He will count the number of threads in horizontal and vertical direction within the canvas, and so establish what we call a canvas fingerprint. If we're able to relate these different fingerprints to, if we're able to relate that fingerprint to the fingerprint of another painting, we can draw conclusions about authenticity. We can, for example, say that they were painted by the same artist, or at least during the same period. And this is a canvas fingerprint that was obtained by an automatic. This is an automatic canvas counting algorithm. But we wanted to do something else. Instead of counting threads, we wanted to look at the texture properties of the canvas. And this is during one of our visits at the Claessens company, that still manufactures canvas in a traditional way. It's in Waregem, I think. And our X-rays were acquired at the academic hospital here in Brussels by use of a mammography device. And this is the data itself. So each column here is of the same type of canvas. So this is the same type, this is the same type, but differently processed. So the first column corresponds to canvas, raw piece of canvas, so the raw cloth, so unprimed, unprocessed. The second row and the third row correspond to primed pieces of canvas, meaning that they were coated with a base layer in order for the artist to use and to paint. So in the first instance, we asked ourselves, is it possible to extract features with which we are automatically able to determine these different types of canvases? And in a second step, we asked ourselves, are we able to extract features in such a way that we're able to retrace the origin of a piece of canvas? So for example, these are 9 pieces of canvas of the same type, but they come from a different source. So we asked ourselves, can we do this determination? Can we find that out? The features we use here are first of all frequency-based, in which we identify the main frequencies within the image, in horizontal as well as in vertical direction. The second set of features are called co-occurrence matrix features, which gives us the co-occurrence grayscale values, pixel values at a certain offset within the image. So this is kind of a histogram, basically, of the image. The third set of features is a very powerful and widely used texture descriptor technique, which are called local binary patterns. And let's jump to the results immediately. So in case of classifications of different types of canvas, we see that we have very nice classification results of 90% and above. In the case of trying to find the source of a piece of canvas, in case of the unprimed piece of canvases, this does not make any sense because the cloth is too mobile. We cannot, it moves too much, so we cannot acquire them in such a way that we can extract features, consistent features for these pieces of canvas. Now, in case of primed pieces of canvas, apparently the priming process characterizes the canvas itself, and you can see that we're again able to have some pretty good classification results. Even in the case where we have very blurry pieces of canvas, we have 80% classification rate and above. The next application I worked on is the segmentation of multispectral images of paintings. So I talked before about multispectral acquisitions of paintings, and here I will show you how a painting, again the portrait of Susan Bambridge, changes across wavelengths in the electromagnetic spectrum. So you see the painting changing while the wavelength changes as well. And notice that the lips and the face of the portrait become brighter as we move towards the red wavelengths of the painting. So let me go through that again. So notice the lips and the face. So, and you can also see that in the infrared part of the spectrum, so this is an infrared wavelength, you can see a lot of stuff happening here. These are all restorations that were applied to the painting. So now a pixel is not characterized anymore by 3 color values, but it's characterized by a whole curve. So, and the segmentation algorithm was developed in such a way that it classifies these curves and segments the image. So for example, here there's a little test patch taken from that painting. The algorithm decided that there were three main different types of green, so three segments of green, and these are the representative spectra in the electromagnetic spectrum. If we apply the algorithm on the entire painting, you can see that the algorithm decided there are three main colors, three important colors that make up the painting, together with the respective spectra again. So why do we use this segmentation algorithm? Well, we did some initial tests in order to try to detect automatically restorations. So and here you see a part of the painting, a regular photograph. Here you can see the same part but under infrared light. And this is what our segmentation algorithm does. It identifies this weird segment as being a restoration. So this is a zone where we applied some mastic. So the substance that is used to fill in these cracks. And as a last topic, I would like to talk about the characterization of jewels and beads within the Ghent altarpiece. So one of the objects that is present in most of the panels of the altarpiece are these type of jewels and beads and all these kind of objects. So the idea was here to try to find a way to compare all those objects with each other, and so did make an assumption about how consistent were the Van Eycks when painting these different objects within different panels, and how different are these pearls with those of their copyists, for example. So, but before we can compare pearls, we need to extract them. And this is a toy example that I would like to show you how this pearl detection algorithm works. It's called the Huff transform. So this is a toy example where we have one pearl. This is an edge image, which nicely shows the edges of that pearl. And then the Huff transform, what it does, it will trace, in each of these edge pixels, it will trace a circle. And so we do this for all these edge pixels, and you can see that these circles nicely intersect into the same point. And this point is a maximum in that image, and it actually corresponds to the center of the circle we wish to detect. So if we put this as the center of the circle of a certain radius we wish to detect, and if we superimpose our original, you can see that we nicely segmented out that pearl. So we can do the same thing on an image of the Ghent altarpiece, such as this. This is after we apply this Huff transform, where each of these maxima correspond to the center of a pearl. And these are the pearls we were able to detect of a certain size. Now, there are still some false positives. There are still some things we see as a pearl that the algorithm sees as a pearl which are not. So we need a post-processing step that takes a number of features into account. For example, a pearl is something that is very smooth. The surface is very smooth, which is something we are able to characterize with image processing techniques. We're able to locate this reflective spot within a pearl. We're also able to calculate the area of that reflective spot. We could extract a number of grayscale statistics with which we can make this elimination of false positives. And then the part that characterizes these pearls was done in collaboration with people from the Ghent University, Liliana, which is also present here today. And she uses the concept of spatiograms. So spatiograms extend the idea of histograms by also including an idea about the space, the location of these grayscale values within the image, which is something that regular histograms do not. Then there were some metrics that were developed to be able to compare these different spatiograms with each other. And the conclusions of this study were that the pearls of Van Eyck throughout the entire altarpiece were extremely consistent. While if you compare them with those of their copyists, that there is a substantial difference, which translates itself in the values of the metrics that were developed. So, and this last slide is the very initial work on trying to Van Eyckify paintings that were not made by Van Eyck. So, for example, here you can see a Van Eyck pearl. These are pearls of their copyists, and this is after we apply that transform. So you can see that they nicely match the pearls of Van Eyck. So this is a very initial work in that context. And these, so to conclude my talk, these are my contributions. To sum up, I developed two visual aids for art experts. One for the removal of canvas that is being used for restoration of the Gauguin painting I talked about. The cradling removal will be done together with Rachel Yin at the Duke University in the context of the Guessy altarpiece. We introduced two novel crack detection methods. One that will be used during the restoration of the Ghent altarpiece. It can be used as input for a digital restoration algorithm. We proposed a canvas characterization method that goes well beyond common thread counting. We proposed a multispectral image segmentation algorithm that shows very promising results for detection of anomalies or restorations. I was involved in projects around jewel characterization and brushstroke analysis. And together with a colleague here at ETRO, Gabor Fodor, we did the stitching and the registration of very high resolution and multimodal images of the Ghent altarpiece. We're still involved into a number of ongoing projects and collaborations, so we will continue our collaboration with the Royal Museum of Fine Arts here in Brussels. I will work together with Ingrid Dobeshi and Rachel Ying on a large-scale project about a Guessy altarpiece, so together with people from the Duke University and the North Carolina Museum of Art. I will continue my work together with the people from Ghent on the Ghent altarpiece, and we were asked to be a consultant for the new acquisition project of the Ghent altarpiece while it's being restored. This concludes my talk. If there are any questions, feel free. Thank you.